Hey, welcome to the first in the series of Trig Identities. This is part one. And trigonometric, I guess, we're pretty familiar with that. The sine and cosine and tangent stuff. What's an identity now? An identity is a relationship in maths, which is true for all values of the variable. So we're going to try and connect sines and cosines and tangents too later on in relationships or equations that hold true for all values of the variable. And of course, here, trigonometry now has been expanded from the SOHCAHTOA to our unit circle, and so we're going to use that to see if we can make connections between sines and coses of angles in different quadrants, and also between, positives and negatives. So there's a couple of relationships over here. There's one, sine squared plus cos squared equals 1. Do you believe that? The cos of, over here, the negative angle is equal to the cos of the positive angle, but the sine of the negative angle is minus the sine of the positive angle. Oh, well, that's interesting. And the cos of 90 minus theta is the sine of theta. The sine of 90 minus theta is the cos of theta. So there's some interesting stuff going on there. So what we want to do is see if we can prove some of these relationships. And a good question to ask, say, Huddy, why are we doing this? I think that's a good question in all your work and all your sort of study now, to ask why you might be doing something. Well, maybe I could give you a little hint by saying, what if we had something like 3 sine squared theta take cos squared theta, and we might be wanting to simplify that. We might be trying to solve an equation. Would it be beneficial, do you think? I think so, to actually remove this and get it in terms of sine. You could say, cos squared is 1 take sine squared. If, only if, come over here, up the top here, left up here, only if we can establish that. That would then produce an equation on the or an expression on the left, with only sine squared in it. Now that could be useful. That could be useful. So that's where we're headed. Let's try to simplify expressions in sine, cos and tan using identities. Come on down, let's try and prove some now. Okay, so here's some little unit circles. I'll just go up a little bit, might need this little room here. Okay, so come to the first one here. This is a unit circle. Let's draw in what we know. Okay, so if that's theta, then we've said the point P there has an x and y value, and the y value is the opposite over the hypotenuse, which is 1. So the y is sine of theta, and the x value is this side here. So x, if you like, if you did x over 1, that would be the cos of theta. So that's what we've been saying. That's our new explosion. SOHCAHTOA has exploded into a big new area here of circular functions, if you like. So let's write this triangle out separately here. So if we do that, hypotenuse is 1, this is x, and this is y. By Pythagoras, the square on the hypotenuse equals the sum of the squares on the other two sides. And there we have it by Pythagoras. And of course we've said that x is the cos of the angle and y is the sine. So we've just established our first trig identity. Nicely proven. Okay, and so we could put as required in brackets if we were told to actually prove that. We've actually gone and done a nice little deductive proof there. Let's go to the next one. Let's come to this one here. And what we're trying to do, well, we've lost that a little bit there, so let's just come up. We'll just find it again. Here it is. It went over there, mate. All right, come back. So here we've got one to play with, and this is the relationship between the cos of a negative angle and the cos of the positive angle, and similarly the sine. So let's look at this diagram carefully. They both have a theta in there. There's one, there's neg theta, a positive and a negative angle. Hypotenuses are equal. Then they've got right angle triangle. So these two triangles are congruent. And the reason for that is angle, angle, and corresponding side. Okay, so let's have a look. What can we do? Well, they have a common side in there, don't they, which is the x values. The x is common, if you like, in there. So that implies that the cos of theta equals the cos of neg theta. These two x values were the same. Let's look at the y's. The y from this one, sine of that theta, is equal to, well, it should be in size the same as that because the triangles are congruent, but this is a negative here, isn't it? So it's minus the y value of sine of neg theta. And again, we've just shown it, so we have as required again. All right, problem solved there. Let's have a look at this one over here. We want to try and hunt down 90 minus theta. So that's that angle in there. So we have the cos of 90 minus theta would be the x coordinate, the sine of 90 minus theta would be the y coordinate. All right, so they both have a theta coming back from there and a theta there. Let's make congruent triangles again. Okay, so let's make these triangles across here. Are they congruent? That's a bit wonky up there. Okay, well, what can you say we've got? Well, we've got hypotenuse is equal, we've got, hypotenuse is equal, there it is, 1 and 1. So hypotenuse is equal, we've got a common angle again, and a 90. So we again have two triangles which are congruent. Same reason, angle, angle, corresponding side. We've just got to be careful with the matchups. Okay, let's have a look now. In this triangle down here, the y value equals the x value, see that? That side's corresponding, equals the x value. I'm using p dash and x dash. And here, the x of this one is equal to the y of the other one. So this is the matchup of corresponding sides. Therefore, what are we saying? Y is the sine of theta, and it equals x dash, the cos of 90 minus theta. And the x in the original one, which is the cos of theta, equals the y in the other one, the sine of 90 minus theta. Okay, and we'll put as required again. All right, just a short proof. This is a little bit rough around the edges here. We should label the sides and refer to them more precisely. But you get the idea. Here we're saying that the sine of 60 would be equal to the cos of 30. Now we already know that from right angle triangle work, because the opposite over the hypotenuse for a complementary angle will be, that's one in a 90-degree triangle, will be the adjacent. Let's see if we can look at that. I think that's important. This is 60, that's 30, and 60's opposite is 30's adjacent. And that's where we get this switch around. Okay, so if they add up to 90, we get that switch between sine and cos there. Think about that one. You've seen that before in actual fact. You might not have remembered it. Let's go down and see if we can do some simplifications. This is from Hayes and Harris Publications, and I want you just to do some simple stuff. This is not using identities. The idea here is if you've got x plus x, it'll be 2x. So I want you to treat sine and cos as just values which are varying, and if you have one cat and another cat, you've got two cats. Okay, have a go at that. I'll show you the answers down below. We'll just do one more piece of theory in between and then do another question. Okay, let's have a look. We're going to play with this. Sine squared plus cos squared is 1. We've established that. So that could be replaced by 1. 1 could be replaced by it. Sine squared, these are all the useful rearrangements that you can do to simplify expressions. I showed you one before. Sine squared could be replaced by 1 take cos squared. Or 1 take cos squared could be replaced by sine squared. That's to make common terms, if you like, in an expression. Cos squared could be rearranged 1 take sine squared, and so on. So you get the idea. Let's do some and see how you go. So come down here now. Example 22 here. Simplify 2 take 2 cos squared theta. Well, you could play with cos squared and call it Well, first of all, let's factor out the 2, common factor, and then 1 take cos squared. You play with 1 take cos squared and call it sine squared. And you usually put that up there as cos squared plus sine squared equals 1, giving a reason. So it's a lot simpler, isn't it, than that? Just to say, well, that's 2 sine squared. What about this one over here? You could take out a common factor of cos, because that's cos cubed. So if you do, this becomes sine squared. What would you multiply cos by to get sine squared cos? It would be sine squared plus, and then multiplying by cos squared to get cos cubed. Oh, and look what's happened in here. Sine squared plus cos squared is 1. So you could put there, since sine squared theta plus cos squared theta equals 1. We tend to put that in if they ask us to show that. So we give reasoning, so we're not guessing. So it's not a show that here, it's just simplify, but it's worthwhile putting in mathematical reasoning along the way. Have a go at a couple, so come down here, and here's question 2, the answer's below there. So maybe do alternate parts, or you could try all of them. The basic aim, though, is to, I suppose, get, if you try to put it in simple terms, have only a single trig function involved. Okay, so that will simplify it. So get either all sine squareds or cos squareds there. Okay, that's the idea. Have only a single trig function, makes it easier to understand the function. Let's have a look at some answers. And here we've got question 1 and 2. So how did you go? Mark your work, make sure that you got it right. You can see how what seemed to be a complicated function in 2 part A just came down to the number 3. So that was worthwhile doing, wasn't it? When the expression looks complicated, but it actually isn't in real terms. Let's go down and build a bit more here, our ability to rearrange. So here we are, simplify if possible, cos theta take sine theta all squared. So cos and sine are just going to be numbers, aren't they, for specific values of theta. So let's expand this as if they are ordinary terms. First one squared minus twice the product plus the second one squared. And then, of course, oh, look at this, cos squared plus sine squared, put it out the front because that's a 1. And then we've got minus 2 cos theta sine theta. Later on, we'll actually be able to replace that as well. Well, that's an excitement for later on. And here's a good reasoning piece here, using the perfect squares expansion. All right, pause the presentation, have a go at these. Start to think, hey, I'm getting quite powerful in understanding complicated expressions by simplifying them first. Let's have a look at the answers. Here they are. Did you get those? Okay. All right. Let's go on. Let's build up some more tools here. Here's another little example and some exercises for you. Factorise. Okay, so factorising could be important if you're trying to simplify an expression. Okay, so this is a square minus a square. A sine and cos just behave like usual terms, they're numbers. So this is the first plus the second, first minus second. You've got to know this. Your difference of 2 squares from year 9 and 10. A squared take b squared. And this one, oh, that's a quadratic. Okay, here's the rule over here. And there is a little tool you can use if you can't see that this is sine squared and then that's the single term. You could let p equal sine theta, and this becomes p squared take 3p plus 2. That might help you see how to factorise it. P take 2, p take 1, and then replace the p by sine. So that's a little tool. But what we're saying now is we want to gear up, because what if we had something like this one, and we were dividing by sine theta take 1. Let's put it over here. Sine squared theta take 3 sine theta plus 2 over sine theta take 1. That looks like quite an animal. But you can factorise this and then cancel sine theta take 1. And, because you would have factorised this, with a proviso that sine theta was not equal to 1. So you can do some simplification later on with quotient expressions if you're able to factorise. Okay, pause the presentation and have a go at some of these here. I think you should do at least every other part. All right, come on now and let's build a bit further. Here's some answers for you, and we're able to do those. If you're not sure, go back and try again. Talk to your classmates, talk to your teacher, try and suss these out. Okay, let's go on. Here we go. More of the same stuff here. Can you do it? You can see the point now. Can we simplify this down? Well, yes, you could. First of all, take out 2 as a common factor. What do you multiply 2 by to get 2? It's 1. Take, because that's a take. What do you multiply 2 by to generate 2 cos squared theta? It's cos squared theta. And then difference of 2 squares again. And lo and behold, it's just what I said up above. You've been able to cancel it. So this quite animal of an expression is really only 2 lots of 1 take cos theta. And you've done well to understand that. What about this one? This looks a bit hard. So you can see in the bottom line it's a square minus a square. We'll later find out another way of writing that. But here it's first plus second, first minus second. And it cancels. So that's 1. So it's 1 over cos theta plus sine theta. All done. Okay, have a go. Here's yours down here. Question 5 and 6. Okay, so here, how can you see that to show that? Now these are dangerous because you are given the answer. So every step you take, you must justify. Otherwise, people will accuse you of fudging it to get the known answer. Justify each step mathematically. Okay, that's important. Put the reason in brackets. And then at the end, when you've concluded, in brackets, as required. That's the latest way of saying it. There used to be, in the old days, QED, which meant quod erat, this is for signing off, demonstrandum, which was required to be demonstrated. You'll see that in older textbooks. Or RTP, required to be proven. It's been customary in the history of mathematics, when you're asked to prove or show something, to sign off with one of these. Okay, this is the modern one here, but that's the history. If you ever see those other ones in books, then that's the sign off. Okay, so have a go at 5 and some of 6, and I'll show you the answers there. See what you think. There's 5. And there's 6, well, we haven't got fully worked solutions here. You could also just have a look at what Hayes and Harris have done here. You could try to graph both of those functions, this one and this one, and see if they come to the same graph. That's a simpler graphical way, not as good mathematics though. All right, how are you going? Let's do some more, not much more here before we move on to the next presentation. Okay, we're going to practice these now. The cos of negative angle equals the cos of the positive angle. The sine of a negative angle is minus the sine. Remember that congruence proof up above. The cos of 90 minus theta is equal to the sine of theta. The sine of 90 minus theta is the cos of theta. They switch around. All right, the side adjacent becomes the side opposite, therefore angles in a right angle triangle, complementary angles, the ones that add up to 90. All right, let's have a look at an example of how we can use this. Okay, simplifying 2 sine theta plus 3 sine theta. See, the argument or the angle involved in sine there is different, so let's see if we can remove it. 2 sine of neg theta. The sine of neg theta is minus the sine of theta, and plus 3 sine theta. So you could put that in brackets. Sine of neg theta equals minus the sine of theta, giving a reason there. And then finally, you've just got sine theta. So that was useful. That didn't look to be that simple, but it is. There it is now. 2 cos theta plus cos of neg theta. Okay, 2 cos theta, let's leave it. Let's play with this. Cos of neg theta equals the cos of theta. So that's our reason in brackets for making that replacement. Not so necessary here because we aren't given the answer. We aren't told to show that's a certain expression. but it's still useful to explain the mathematical simplification going on there. So this is 3 cos theta. Can you see the power of these identities in trying to understand better the function we're given? So this, we can talk about what's the maximum and minimum value of that function. It's easy because it's a maximum and minimum of 3 cos theta, which would be positive 3 as max and negative 3 as min. Get the idea. It's very useful when you've got a complicated looking function to simplify it and then perhaps discuss it. Okay, I want you to have a go. I think you should do all of these. So pause the presentation and have a go, and I'll show you the answers. Okay, so there they are. How did you do with those? Right, let's move on. A little bit to go now. Just another little simplification here. Okay, so this one is using pi on 2 minus the angle, or 90 minus the angle. So write the problem down, and we're making a replacement. Sine of 90 minus theta is the opposite. It's the cos. So we could put here, since sine of pi on 2 minus theta equals cos of theta. Okay, and now we're all in cos theta land, so it's 5 cos theta. All right, so using that last one now, have a go at 2 and 3. I think probably do all of them here, just to, because we haven't done many using this idea, okay, of changing the sine or cos for the complementary angle, for the other angle that adds up to 90. All right, let's go down and look at the answers now. Okay, there are the answers. And how did you do? Are you feeling powerful now? I think you should, because we're building up some powerful identities here. All right, so that's the first of 3 presentations looking at relationships or identities between trig functions. Cheers for now. I'll catch you in another presentation.